Isn't 1 radian equal to 1 radius length?
Well, you got to be more specific than that. So yeah, it has to do with 1 radius length, but you got to be more specific. Yeah.
Isn't a radian? I was just gonna say the radius length, but like to the circle, like how many pieces of the radius have been put into the circle?
Okay. All right.
It's like the arc length that subtends 1 radius length.
Okay. So, so here I'm showing. So that's 1 radius length, and so then here I'm showing, say, 2.3 radius lengths of all 3 arcs. So my arc length, so this is 2.3 radius lengths. And again, no matter what circle we look at, it's 2.3 radius lengths of the circle of radius 1. It's 2.3 radius lengths of the circle of radius 4. It's 2.3 radius lengths of the circle of radius 6. And so that number of radius lengths is then equivalent to the angle measure in radians. That's where radians come from. Okay, so radians are a very convenient way of measuring angles because they relate to the length of the arc. And so when we're dealing with situations and applications and we're measuring all these lengths, when we have angles involved, then radians gives us this bridge to distance, right? Because it's measuring arc distance in the units of radius length. Okay, so how could we define, so here we are 2.3 radians. How long is that arc in coordinate units? So we call that S. S is true arc length in coordinate units. So how can we find out what the length of that red arc is? What we call S, or the arc length. I know Christian knows. And why would, so you want the angle which is 2.3. And can you explain why that works?
Because it's the opposite of finding an angle.
Okay. So you're like switching around the equation? Okay, yeah, you're solving for S in the equation. But how can we make sense of, why does 2.3 times 6 give us the length of that red arc? Yeah.
Because the units of the R is in 6 units.
Okay,
And
so
so if the radius length is 6 units, and you have 2.36 units, then that's how you find it.
excellent. So 2.3 is, if it's the angle, then it's also the number of radius lengths. So there's 1, and then there's 2. So we have 2.3 of these arc lengths that are 6 units long, radius lengths. And I don't know what that is.
13.8.
0.8. So again, this way of measuring angles with radians is really powerful because then it helps us relate then to distances in a situation. Because the number of radians of kind of how open the angle is in radians is equivalent to how many radius lengths are marked off from the one ray to the other. Okay, so let's take a look at, if I zoom in here on that circle of, okay, so just a side note then. So here is, maybe, jeez. Here is 3 radius lengths. So this angle is 3 radians because it cuts off 3 radius lengths of arc length. So that's all fine and good, but it would be really nice to know what is exactly halfway around the circle. So how many radius lengths to get exactly halfway around the circle? So it looks like it is something between 3.09 or 3.1 and 3.2. 3.2 is too many radius lengths. 3.1 is not enough. A lot of you know what this is. Right.
3.14.
The perimeter of a circle is 2 pi times the radius, so half the long would be pi times the radius.
Well, but that's already knowing what pi is. So yeah, you're exactly right. You're exactly right. But my question kind of precedes that knowledge. No, it's okay. That's okay. So there's this number, right? Some number between 3.1 and 3.2 gets us exactly halfway. And so,
Well, couldn't we just go off like the angle itself?
what's that?
Couldn't we go off the angle itself? Because, well, we know the angle is the arc length in radians.
Right.
So I gotta know how to like go from degrees to radians, but could you, since it's 180 degrees, since that's half a circle, change that to radians and then multiply it by whatever?
So you're taking this big detour to just so it's some number of radius lengths between 3.1 and 3.2, right? And it's you all know this number, pi, right? 3.14159. So if I set it equal to pi, look what happens. Okay, so now I've set it equal to, so ignore the scale. I just set n equal to pi, and that gets us exactly halfway around the circle. Okay, so that's what the number pi means. It's how many radius lengths it takes to get exactly halfway around the circle. Okay, so now this first circle that we talked about, let's see if I can, is called the unit circle. Has a radius of 1. Oh, I forgot. Okay, so here are whole numbers of radians. Okay, whole numbers of radians. 1, 2, 3, 4, 5 there, and then 6. And so then all the way around is exactly how many radius lengths. If it's halfway around is pi, all the way around is 2 pi. Okay, and that's where we get the radius, the circumference of a circle. 2 pi times the number times the length of the radius will give us the circumference. So now this is the unit circle because it has a radius of 1. So here's a really powerful idea. How can every circle in the universe, from the circle that an ant would walk in to a circle of an orbit of a planet, every single circle can be thought of as this circle? And that's why the unit circle is such a powerful idea. How can every single circle, no matter how small or how big, be thought of as this circle? And so asking that question is really asking then, what does 1 represent? So what is that 1 mean? If this circle can represent every circle, then what is the 1 about? 1 what? Yeah, 1 radius length, right? 1 radius length. So the circle that an ant makes, 0.3 centimeters, okay? 0.3 centimeters of a radius. That radius of 0.3 centimeters could also be thought of as 1. 1 what?
Radius.
1 radius length, you see? And then, the orbit around a planet. 22, I don't know, trillion miles? I'm guessing. Anyway, imagine a circle 22 trillion miles in radius. Whatever that might be in space, okay? What could 1 be? So 1 still applies to that circle. 1 means 1 radius length, which would mean 22 trillion miles. Okay? So that's why the unit circle is so powerful, because we can think of any circle as having radius 1 if we think of the units of that 1 as radius lengths. Okay? So then what about sine and cosine? So if I have some angle, so here's the angle of 1 point, 1.3. There's an angle of 1.3 radians, which means 1.3 radius lengths, whether that's in a circle of radius 0.3 centimeters or circle of radius 22 trillion miles. Okay? So what is sine of that angle? Nicholas?
The distance above the horizontal axis.
Okay, so sine of 1.3 is defined as then this vertical distance of this final point on the unit circle, which can be any circle, right? It's this vertical distance above the horizontal diameter of that point. Okay, and then the cosine of 1.3? And so what's another way to say the vertical distance above the horizontal diameter in terms of coordinates?
Oh, it's x coordinate? Or no?
That's just the y coordinate, right? So this vertical distance above the horizontal diameter is just the y coordinate of that point. Okay? And then cosine is likewise the horizontal distance to the right. So that's the x coordinate. So let's show that. It works. I haven't used this in a while. There we go. Okay, so get your calculator or graphing calculator, whatever you want, and let's do, so if you do sine of 1.3, you get 0.964. The answer is 0.964. So, what's the meaning of that number? 0.964. 0.964 what?
Radians.
Okay, so radians is,
Radius length.
yeah, so what are we? So we're 0.964 radius lengths above the horizontal diameter, where that y coordinate is 0.964 radius lengths up. So in the circle of 22 trillion miles, how many miles above the horizontal diameter are we? How would you find it?
Times that, times 22.
21.2.
That fraction of 22 trillion miles, you see? And so then the x, what's the x coordinate, cosine of this? 0.2 what?
267.
0.267. What does that number mean? Tell the person next to you. 0.267. What's the meaning of that value?
The horizontal distance from the y-axis. So it's like the x coordinate. So it's like 6 times. So it's 5.9 trillion. The axis. So sine is the vertical distance above the x-axis. Cosine is the horizontal distance to the right y-axis.
So the cosine of an angle is a number of radius lengths, or a fraction, whatever fraction of the radius length that you are for cosine to the right of the vertical diameter, or the fraction for sine, the fraction of the radius that you are above the horizontal diameter. So if you want to know, if the ant is here, right now, the ant, how far is the ant from to the right of the vertical diameter right now? How would you find it?
5.
0.267 times, well, yeah.
Yeah, it would be that fraction of the radius, 0.3 centimeters, would tell you then how far in centimeters the bug is, or the ant is, to the right of the vertical diameter. Okay? In centimeters. And then how far up is he? How far up is he in the circle? That fraction, 0.964 of 0.3, so you multiply. So sine and cosine then is a way of normalizing all circles and giving you how many radius lengths of vertical position and horizontal position that you are in a circle with a radius of 1, which represents 1 radius length.
So what if the at went all the way to pi, like it went half the circle?
Right.
Would that be the cosine of pi, and then we have to multiply that times 0.3?
Right, and what would the cosine of pi be what would the cosine of pi be? It'd be the horizontal distance here in radius lengths. What would that be? -1. So it's defined as, cosine is defined as horizontal distance to the right, so that when you're to the left in quadrants 2 and 3, it's negative. And then sine is defined as number of radius lengths above, so when you're in quadrants 3 and 4, sine is negative by definition. Okay? So these all kind of work the same way. How far has the ant traveled? How far has the ant traveled along the arc? 1.3 radius lengths. And so how far is that in centimeters?
0.39.
1.3 times 0.3 centimeters. And how far up is he? 0.964 radius lengths. So if you want it in centimeters, what do? You take it up 0.3. And how far to the right is he? That's a 9. How far to the right is he? 0.267 radius lengths, or that fraction of 0.3 centimeters.
So would this mean that would only work when he's 1.3 radius lengths of the circle?
Yeah, so you change the angle and you're going to get a whole new set of, it's a whole new location. It's going to be a new arc length, a new vertical and horizontal distance. Yeah, you change the angle and you're in a different place. Yeah.
So is that why they always say, is that where like sine squared plus cosine squared equals 1? Because if you were to multiply those, the circle's 1, so it's 1.
Okay, so yeah, what is the length right there? What is the length of this hypotenuse of this triangle?
Well, theoretically it should equal 1.
It is 1. It's 1 radius length, right? Don't push the button. Okay, yeah, it's 1. So yeah, and so by the Pythagorean theorem, Pythagorean identity is that the cosine, that squared, plus that squared equals 1 squared. Yeah.
Why would the hypotenuse be 1?
What?
Why would the hypotenuse be 1?
Because what is 1 in this? What is that hypotenuse in this situation?
I mean, I know the value, but that's
What is it in? How does this relate to the circle? How does that hypotenuse relate to the circle?
you have to convert it to centimeters. It's still 1 unit.
It's always
It's still 1 unit.
Distance from the center to the circle is what? What's the distance from the center?
At any point.
Okay, yeah, it did click. Okay, I understand.
Okay, so that's your crash course in Trig to help you with these optimization problems you're going to have involving angle. Okay. Any questions? Yes.
If the radius was 2, like instead of 1,
Okay.
would cosine squared, like would the hypotenuse still equal 1 or would it equal 2?
Hypotenuse would be 2.
Hypotenuse would be 2.
Uh-huh.
So that-
Yeah. So, but then, if you wanted that length in the units of your axes, it would no longer be cosine. It'd be 2 cosine.
Oh.
But it would still, the length of that would still be cosine measured in radius lengths, even though your circle has radius 2. But if you're building that triangle with 2, then this length in terms of the axis units is now 2 cosine theta. Okay?
So it multiplies by whatever you multiply in the circle by. So like if say it was 0.3, then would it be 0.3 cosine?
Right.
Okay. So
If you want those distances in your axis units, it's going to be cosine. You have to take cosine that fraction of the radius, and that in those axis units, and you'll get that distance in the axis units. Does that make sense? Okay.
So it's like radius times cosine squared plus, or what's it called? Yeah, it's a plus radius times sine squared is going to equal to the radius.
Yeah. So radius, like this.
Yeah.
Yeah, because you factor r squared out and you just get cosine squared plus sine squared equals 1. So it's all, everything's multiplied by r, so it still works. It's just magnifying the circle. Okay, so try to use those meanings when you're solving the next set of optimization problems. So let's tie some things together with a kind of a different exercise here. Any questions can I raise? So here's a function, and we are going to, I'm going to tell you that this is an accumulation function. Based on all the relationships we're learning about accumulation and rate of change, can we sketch, in the same axes, can we sketch the rate of change function? So taking what we know from the accumulation, all the information we can get from the accumulation, can we put together a sketch of the rate of change? Give it a shot. So take a couple minutes and I'll take attendance and see what you come up with. So using our meanings, our connections between rate and accumulation, can we sketch the rate of change graph? Yeah, just the rate of change of this accumulation.
Oh, you just need to drop the full
Okay, let's see. How did you get started, Melody?
Well, first off, I made a note on the axis at 1.5 on the x-axis, and I can't really see the numbers well, but the maximum on the initial rate function, I gave it the first function had to be above the axis at those points, because it was increasing.
You're looking at the low and the high point of this accumulation, and so at the low point,
That's right there, it has to start becoming positive to the rate, and then it has to start becoming negative at the next maximum.
okay.
And then I just kind of drew a line, I can't see the numbers.
Okay, so one more time, I'm not following. I'm sorry.
At 0.5, it looks like the slope, or the rate of change graph crosses the x-axis.
Okay, so there's a point there.
Yes.
Cool. So on the rate, you bit off a big chunk. Okay. No, I'm not saying what you said was wrong. I just I couldn't put it all together at once, so we needed bite-sized chunks. So you're saying the rate here would be 0. Is that right? Okay, and then?
And then it will be 0 again at that x squared.
Okay.
And it's going to be above the x-axis between those.
All right, so she's saying the in between those, so can someone explain why is it 0 there? Why is it 0 there? Alexander.
Because there's an x and a minimum,
Okay.
and the rate of change is positive.
The rate of change is pausing. Is that true?
Well, the accumulation function also.
What's pausing?
The accumulation function.
Accumulation, it's going down, and then it's not changing for a moment. So the rate of change is 0. It pauses. And then it starts going up. So for a moment there, it doesn't change, so the rate of change is 0. Okay? Same thing with here. It's heading, accumulation's increasing, then it's not increasing, nor it's decreasing, so that the rate is 0. And that's decreasing. Okay, so in between she said it's the rate of change will be above the x-axis. Do you agree with that? In between there?
The rate of change.
Yeah.
Yeah.
Because? Kevin, why?
It's getting, well, in between those, it's getting more positive.
Okay, the rate of change is getting more positive.
Well, it's increasing.
Or, sorry, the accumulation.
The accumulation is increasing, so that means the rate of change has to be increasing as well.
Okay, and when is the rate of change the greatest? Over here?
No, like where it's steepest.
Right, the rate of change, somewhere in the middle here is where rate of change is, the accumulation is changing at the fastest rate.
Yeah.
So we're going to have a high point of the rate of change. Okay, good.
I have a question.
Yeah.
How can you determine whether for point, I was just say that's 2.2. So between those, how come it's not going all the way up to 4 or 1? Why did you make it so?
Great.
shallow?
Okay, so we're graphing the y-coordinate of the black graph is the rate of change of the purple. So he's saying, how do we know it's not way up like this or way down like this? So how can we get a good estimate maybe for that greatest rate of change?
Could we just I think the way you find it is by the accumulation graph, just find the actual derivative at that one point where you think it's the steepest.
How are you gonna? All I gave you was the picture. How are you gonna get the rate of change?
If I have numbers.
Can you take the slope between 2 points here?
Yeah. So what is rate of change? What is our construct or understanding of rate of change? Okay. So remember 4a, small change in x. So our scale here is even, right? Oh no, it's not. This is kind of confusing because changes in x here are, yeah, so given these two scales, how does that change in y compare to that change in x?
Oh, the change in y is a lot bigger.
How much bigger? So if these lengths look about the same, but based on the scale, that change in y, no. Yeah, it's twice as big, right? Because do you see that this x-axis scale is spread out twice as far? So an estimate for the rate of change here would be 2. Do you see that? So it's good point. So maybe it's more like this. Did you catch that, what I did? Besides draw a really bad graph. Okay, so that may be a better. So we said the maximum rate is about 2 right there. And we know the rate is 0 there, and the rate of change is 0 there. Okay, so now what about, wow, one more try. What about before and after this? So what about for x values less than 0.5? What about our rate graph? None.
I think it's negative.
What's that? Negative. Because?
Because the accumulation graph is decreasing.
Decreasing. So it's all over here, it's going to be negative. And then what about greater than this point where the rate of change is 0? Also negative. Because?
It's also decreasing.
What do we think about that? Is that what came up for your rate of change graph? Okay. Now, I'm going to leave that up there. And now go back to the original function. I'm going to tell you that the original function is a rate of change function. This is the rate of change. And I want you to sketch accumulation. So the purple graph is now rate of change. I want you to sketch the accumulation graph. See if you can do it. And just to give you a reference, you need a reference. So let's say that accumulation goes through 0, 2. Okay? So you got the point. At 0, the accumulation is 2. And the purple is the rate of change graph. And you're going to sketch the accumulation graph. Yeah.
like the beginning, like just the first section before it crosses the vertex.
Yeah. You're saying over here?
Yeah, that first section.
Are you talking about the new question or the previous one?
The new question.
New question, okay?
Yeah. Can the accumulation function go like? Does it have
So
to
Kevin,
be
what
this?
is the rate of change? What can you say about the rate of change here?
Well, I know the rate of change is negative. Well,
This is the rate of change graph. So what is the rate of change here?
because it's getting less negative and more positive. But then we're gonna get this positive. The point is to stop there, so kind of like there.
Right. That's right.
That would be a maximum.
Ross, get me started. Tell me something. What did you, how can we start this?
So from 0 to 1, the accumulation is
Why?
because at that from 0 to 1, the rate is negative.
Okay, so he's noticing here, the rate is negative from 0 to 1, so we must be decreasing, the accumulation must be decreasing from 0 to 1. What do you think?
Yeah.
Agree with that? And then keep going. So what about at 1? What's going to happen to the accumulation at 1?
Accumulation pauses,
Accumulation pauses, and then?
and it begins increasing.
Okay, and then begins increasing. So what in the what do we call that with the accumulation?
Oh, it's a local minimum.
He wants a local minimum right there. Agree?
So one more time. What?
Rate, so accumulation is decreasing because rate is negative, and then accumulation increases. So where that rate is 0, there must be a pause, must be a minimum. Something like that. Okay, someone take over from there. Someone who hasn't. Jonathan, tell me some more.
Well, from 1 to 3, the accumulation will continue to increase.
Continue to increase. And what about at 3?
At 3, the accumulation will pause and then begin to decrease.
So at 3 we have?
Local max.
I don't know exactly what it is, but this is what you said. This is what you said? So we have a pause there where the rate is 0. And since the rate was negative, the accumulation is decreasing. And then the accumulation pauses where the rate is 0 and the accumulation increase. So this is what a relative minimum looks like on the rate graph. See that? That's what a relative minimum looks like because your accumulation is decreasing, then 0, then increasing. So relative minimum right there. And then here, the rate's positive, so accumulation's increasing, and then the rate's 0, and then the accumulation is decreasing. So this is what a relative max looks like. For the accumulation, it's what the rate function looks like. Okay, Shayna, last part here. So what's going to happen over here, x less than 0?
So it's decreasing, so it's going to come up to 2, and 2 is also going to be maximum.
So what's the accumulation doing, say, as x increases over here?
It's increasing.
Increasing. So you think this is a maximum here? Something like that? And so, how'd you guys do? Questions? Does it make sense? So the blue is the accumulation if the pink was the rate of change. Its rate of change. And the black is the rate of change if the pink was the accumulation.
Can we go over the, if x is negative?
So what about the rate here? The rate is
Increasing. Decreasing.
all you want to look at is if the rate is positive or negative.
No, it's increasing.
What's that?
The rate is positive then, right?
The rate is positive all through here, if you want, and getting less positive. So the accumulation is increasing, but increasing at a slower and slower rate. See that?
Okay, I see.
You got to practice.
So the blue one is the accumulation function. The pink one, would that be the first rate of change, and is the black one the second rate of change?
So if we wanted, then we could say that. So the accumulation rate of change. So we could conceive that the black one is the second derivative of the blue one.
Yeah.
Is that what you're saying?
Yeah.
Yep.
Can you explain like the relation? I don't understand like what the black one, like what's it used for? Is it just for concavity?
Well, that's the rate of change of the rate of change.
Yeah, okay,
So at those zeros, like there's like
So you like know
okay.
how the rate of change is inflection.
Yeah. So let's have more conversations outside of class. There's one more thing I want to do today. So how about this kind of practicing our understanding of those relationships? Any questions on that? Okay. Remember this? So we're coming full circle to kind of heading towards the big conclusion in the course, okay? What's called the fundamental theorem of calculus, which is going to draw upon 80 to 90% of everything we've done so far. So let's recall what this situation was about. Whoa, sorry. So let's recall what this situation was about. Remember this? So just take 1 minute and talk to the person next to you and try to remember everything you can about what you're looking at here. Go. Yeah. Yeah, right.
That's the rate space. That's a step function. That's yeah, that's like as time goes on, wait.
Well,
It's not exactly. Yeah, those are half a second.
but you build the approximate rate of
And then I have a question for you. Okay, how can you represent the change in the amount of sand dumped from 1 to 2 seconds using the function on the left, and I mean the step function, the black function, okay? And how can you represent the change in the amount of sand dumped using the function on the right? Talk about that. See if you can come up with it. See if you remember. That's the question we asked a month and a half ago or so.
Minus the and then for that just gives you the rate, right?
Okay, so hopefully you remembered that on the left we have our rate of change. Rate of change, and that says it right there. Okay, rate of change of weight is a function of time. And this is an approximating step function for that with these 5 rates, R1, R2, R3. What is delta x in this case? What's the change in x we're using to build the step function? 0.5. And then we get our piecewise linear accumulation function based on those step rates, which is doing its best to model the accumulation of the sand over time. Okay? But it's not exact because it's based on our approximating rate function, right? So it's an approximating function. So how can we use that step function to represent the change in amount of sand dumped between 1 and 2 seconds? Aaron?
Would you take the rate, the rate from 1 to 1.5,
R3.
R3, and add it to R4?
Add the rates. Does that give the amount of sand dumped if you add the rates? Yeah, Alexander?
You need to also multiply it by delta x.
Yeah, R delta x, right? R delta x gives little changes in y, right? K delta x plus K delta x. All right, what about over here? How can we, so that would answer that question, representing, what about over here? How can we represent the change in the amount of sand dumped using this function? Christian?
It would be A2 minus A1.
He wants A2 minus A1. Agree with that? All the sand accumulated up in the first 2, seconds, minus the amount of sand that accumulated in the first second gives you that change in weight. Okay? Now I want you to do the same thing again for, what if delta x was 0.000000000000001? Can you represent the change in the amount of sand, change in the weight of the sand from 1 to 2 seconds? Melody?
For a question about the right graph, could you have done A2 minus A 1.5 plus A 1.5 minus
Mm-hmm. Yeah, but then you're just your A1.5s are 0, right? They just cancel out. But it works. Yeah, you're breaking that up. Right, yeah, it'll work. Okay, what about representing using delta x is 0.0001? Do you remember how to represent the change in the weight of the sand?
Is it the smaller?
You want to write that out? How can we represent it? I can represent it in this much space. Chloe?
Would it be the integral of r of x dx?
Okay.
Well, r of, yeah,
Do something else.
yeah,
Is
somewhere.
that it?
Yeah. Well, from 1 to t.
That's right. And so that, if we had our true accumulation function, so this is the approximating accumulation. If we had the true accumulation function then, it would equal F2 minus F1. Okay, so this is a glimpse at where we're going. We'll talk more on Monday.